Hello students, in this video, having constructed the natural numbers, addition on the natural numbers, and multiplication on the natural numbers, we can now proceed to our construction with the positive fractions. We define for two natural numbers and an m, a positive fraction and we're going to find negative numbers at the very, very tail end of this construction. So we're just going to focus on positive things for the time being. We're going to add in 0 and define negative numbers later. But for the time being, I know the ratio of two natural numbers is going to be a positive fraction. By the symbol, m over n. So this is what's going to be defined as a positive fraction, okay? And then we're going to define a notion of equivalent fractions. So here's a definition for us, and this is an important definition. Two positive fractions a over b and c over d are equivalent if a times d is equal to b times c. So that's what it means for two fractions to be equivalent to each other. And we write, so our notation for this, our notation is that a over b is equivalent to c over d. Now let's discuss several properties of this notion of equivalence, right? So here's our first fact about equivalence. Here's our first proposition. It's a silly proposition. It says that a over b is equivalent to a over b. And the proof of that is simple, because a times b is equal to a times b. In this case, b times a, as it's written by our definition over here. So the commutativity of multiplication doesn't really change anything. Great, that's our first proposition. So a positive fraction is equivalent to itself. The second proposition we have is that if a over b is equivalent to c over d, then c over d is equivalent to a over b. Again, this may sound simple, but let's prove it, right? Proof, we can suppose that AD is equal to BC by assumption, right? And then my question is that, then I would like to say that is, does this imply that C times B is equal to D times A? Well, certainly that does. I can just, the order of multiplication doesn't matter. Multiplication is commutative, so this is certainly true. So this proposition is proven. 1, 2, 3, 4. And then the final proposition we want to have is this proposition. It's one of the more interesting ones. It says that if A over B is equivalent to C over D, and if C over D is equivalent to E over F, then A over B is equivalent to E over F. So let's prove this. So here's our proof. Well, the first statement over here is we have that AD is equal to BC. That comes from this statement over here. And it's also true that C times F is equal to D times E, right? And so we would like to conclude something about AF and BE. Well, now what I can do is I can consider now this number, I can multiply this. So let's consider now, consider ADCF. Again, I'm not writing down any parentheses or any, don't really care so much about the order or the parentheses, because I know that multiplication is commutative and associative. We've already proven that for the natural numbers. So now we're really heavily relying on the fact that multiplication is commutative and associative, so that this expression makes sense. Then ADCF is equal to what? Is equal to BCDE. Now, from our cancellation properties of multiplication, what do we know? We know there's a C on both sides of the equation, and there's a D on both sides of the equation. So by our cancellation results, so by our cancellation theorems, for the natural numbers implies what? Implies that a times f is equal to b times e, and this expression is exactly equivalent to saying that ab is equivalent to ef. So these propositions may seem straightforward, but two things to consider. We are relying heavily on what facts? Heavily on properties of the natural numbers that took us a lot of time to prove and followed from the piano axioms. The second thing to consider over here is that now I have three statements. I have that a positive fraction is equivalent to itself. That gives me one property. I have that this relationship, this equivalent notion of equivalence is reflexive. If one positive fraction is equivalent to another, then the other is equivalent to the first, and it's also transitive. So this is a reflexive property, and this is a transitive property over here. So this property is transitive. Okay? And so this shows us that this notion, we can conclude that this equivalence notion is actually an equivalence relation. There's an equivalence relation. And we know from set theory that once you have an equivalence relation, you can put positive fractions, all positive fractions that are equivalent to each other can be put into one class. So there's going to be an equivalent class of equivalent fractions. And we're going to use that equivalence class to define what a rational number is. Thank you very much.